So we are done with all the models for regular language, and the next phase is to study the closure properties and pumping lemma for regular language. But before going into those topics, perhaps it's better to go through some problems. So if you see the book, we have finished I think chapter 3, and then after that we have some problems. And this Hofcroft-Pullman book has many interesting problems, and many of them are quite hard. So you will see this star, double star problem. So you can try those things, and it's fun. If you can solve that, it's a fun in itself. But in the current setup, I won't be able to discuss too many problems, but at least let us go through some of the chosen problems. So okay, here is one. So this is a kind of a toy. You can drop marbles through this these two positions, and this marble will roll down this pipes or whatever. And when a marble hits one of these switches, so it will. So if it is in this position, then the marble will go this way. Okay, but if it hits this, then the position will be flipped. So it's this way. If a marble hits this, then this switch will be turned this way. So the next marble, if you put it here, then it will go to this side, and again this will be switched. So the current orientation of a switch determines where the current marble is going, and once it is hit, the position is flipped, and that happens for all these three levers. Okay. And so given this, what sort of input can you provide? So either you can drop a marble through this A or through this B. So there are two kinds of action that you can take, and those two actions are denoted as this 0 input and 1 input. So marble in A is 0 input, marble in B is 1 input. Okay, so now you can consider a sequence of actions. So that will be a sequence of 0 and 1. So that will be a string of a 0 and 1. And the language we are interested in is all the sequence of inputs if the last marble comes out of D. Okay, so the marble can come out of C or D. So depends on how you drop these things. So if the last marble comes out of D, we take that sequence of input. So that is in our language. So this is how we define this language of a 0 and 1. So you have to construct a DFA which models this thing, and through which you can find the language. And then it asks you to construct a milli machine. So now there is no question of just yes no. So what does milli machine do? If you remember, it outputs some output symbol after each input symbol, right? So the output symbol is the C or D. The opening through which the marble leaves. So you drop a marble, and if it leaves through C, it immediately outputs C. If you drop it here, it outputs D. So after each input, the input is either 0 or 1, you get output which is either C or D. So the output alphabet is CD. So the task is to construct a milli machine with that sort of output alphabet. So now you start with this configuration. So you remember the language we are trying to accept is this, the sequence of inputs for which the last marble comes out of T. Okay. So this is your initial configuration of this machine, right? This toy. Now suppose you drop a marble through this A. So that means one input, right? So let me see. Sorry. Okay, so the marble at A is 0 input, the marble at B is 1 input. So I just messed up. So this will be 0, this will be 0, this will be 1. Okay, so this will be 1. So anyway, I mean, if you put a marble at A from this configuration, so it will come here and then take this path, right? Because the switch is in this way, so it will take this path, so this path. But since it hits this lever, the lever will get switched, right? So now if you put another marble here, then the marble will take this path and then take this path and then go this way, and in that process it will switch this lever and it will also switch this lever. So that will happen in the next thing if you say give it through say A. And if you input 1, that means if you put the marble at B, so then it will take this and then this and then this, so it will take this path, but since it hits these two levers, the two levers will be flipped, right? So now instead of drawing this whole thing, we can just so what are the information that we need here? So the position of the levers, right? So we say that it's in the left position. So here the positions are say left. Here the positions are left, right. So LRR, and here right, left. So RLL. And also in this case we mark this thing. So the output gate through which the last marble left. So here there is no question of last marble because this is where we start, so there is no marble before this. But if we drop a marble and we come here, so through B, so here we know that the marble left through C, so that is why we are left with this configuration and the marble left through C. So this whole level kind of describes what happened during this transition, right? And similarly here also it leaves through C. So yeah, so for example here now if you drop something at B, so that means that will be called input 1, right? So if you drop something here, so then it will take this, right? So it will take this sort of this thing. So this is B, and this will be D, and so this x1 is already in this left position. This will be flipped in this position, and this will be this. So it will be left, right, left, and this is D. So this will be say left, right, and then D. So this is the next configuration that you reach if you are here and if you are providing input 1. So you see this transitions. So how to calculate this transitions. So how do we model this as a DFA? So first of all, what is our input alphabet? Our input alphabet is 0, 1, right? So 0 means a ball at a marble at A, 1 means a marble at B, again. So here it's from, so this should be 1, and here this should be 1, and this should be 0. Okay. So our states are like this. So all possible combination of left, right, and then here we can have either C or D. Okay. So all possible combinations you can put in this, and this is where there is no output thing, because this is where we start. So already you know the start state. So the start state is this one, right? This configuration. And as I said, you can figure out all the transitions, so that you can say that's our delta, the transition function, right? And that's it. This is what you require. So the sigma, q, delta, start state, and what are the final states? So you remember the language we are trying to recognize is the sequence of inputs where the last marble comes out of D, right? So that means we want to end up in a state where this thing is D, right? So all state of this one. So these are just left, right, some combination of left, right, and this has to be D. So all those states will be final states. Okay. So this is the DFA part. And what about the Mealy machine? So in the Mealy machine we do not have final states. So you remember, Mealy machines do not have final states. And Mealy machine's output, when does it give you output? During the transition, right? So Moore machine gives you output after reaching a state. So but here the output is emitted during the transition. So if you remember, we had a function lambda for Mealy machine which has this signature. So you are in current state somewhere, and then you are seeing a current symbol, and you are making a transition depending on this 2, and during this transition you are outputting either C or D, which is our output alphabet. Okay, so this CD, this is our output alphabet for Mealy machine. And then what do you output? See, you are in some state. So for the last ball, exited through this, say, Y. So this Y and Y prime, they are either C or D. So it is something here, and these are some combination of left and right, this RL, right? This is the case. So these are some combination of RL, and this is either C or D. And from here you are making a transition. So this A is either 0 or 1, right? So this A is coming from sigma. So A is either 0 or 1. So, and the next state is this. But if this is the next state, that means the ball left through this, right? This Y prime. So that is the output. So the output should be the C or D through which the ball left. So this should be the output. So this is the output. Okay, and this is a current state. This is a symbol on which you are making the transition. So this is same as this delta, and this is the output. So this is how you construct a Mealy machine. Okay, so let's go to the next problem. So again, it's asking you to construct a deterministic finite automata. So it's a DFA. It's a DFA. Over this input alphabet 0, 1. Okay. And what is the language? The language is such that, so the set of all strings such that every block of 5 consecutive symbols, okay, contains at least 2 zeros. So what is this block of 5 consecutive symbols? So suppose this is your input. Okay, So you just break it down into blocks of 5 symbols. So first 5 symbols, second 5 symbols, third 5 symbols, and so on. So in each block, so this may not be a multiple of 5, but whatever is here, I mean, you just make a block of 5, 5, 5, 5, 5, and the last block may contain less than 5. That's okay. So in each block, what should happen? So it contains at least 2 zeros. So in this position, you should in this block you should have at least 2 zeros. In this block you should have at least 2 zeros. In this block you should have at least 10 zeros. Okay. And this is what my DFA is. Now, how did I come up with this DFA? I mean, it has so many states, 12 states. So now, what is the idea? You see, as I said, you need to assign some kind of meaning to your states, right? And the meaning that we have here, first of all, you see that if you start here, then after processing one symbol you are either here or here. After processing 2 symbols you are in one of these states. After processing 3 symbols you are here. So these things correspond to what is the symbol that you are processing in your current block. So after processing this 5 symbol, then again you go back here or here. Yeah, so the first meaning is this, that if you think this like columns, so say this is the 0th column, so this is the first column, second column, third column, fourth column, fifth column. So after processing, say, I many symbols, you are in the ith column in the current block, of course. After you process 5 symbol, again you go back to the first symbol, second symbol, third symbol. So this is what is this columns mean. And then what does this row mean? So this means, see, in each block you are supposed to see 2 zeros, right? So this row means you haven't seen any zeros in the current block. This means you have seen only 1 zero in your current block so far. Okay, and this means you have seen 2 zeros in your current block. So that is why all the states here are final states. Okay, so this is written here. So this states are either this x, where x is ABCD. So this x means that the finite automata has seen no zeros in the current block, and this x1 type of state. So this means that the finite automata has seen 1 0 in the current block. Okay, so this current block is important, and this type 2 states are like it has seen 2 zeros in the current block and no zero. Okay, so this is the meaning. Now once you have this, it's very easy to put the arrows, right? So here you are, so that means you haven't seen any zeros, and then you have 1, so that means you still haven't seen any zero, but you are in the first symbol. So you go here, and if you have 1, again you are in the second symbol, but you haven't seen any zero. So now after this you haven't seen any zeros, so you have seen 3 ones. So the 2 that are left, that must be 0 0, right? Because you have to have 2 zeros, so 2 symbols are left in the current block, so that has to be this 0 and 0. So that is why there is no edge here from with 1. So if you have a 1 here, that means you reject that thing, so you get stuck and you reject, right? So similarly, if you are, say, here, how can you be here? So you have seen, say, some 1, so maybe you have seen 0 and you are here, or maybe you saw 1 or 1 1 and then saw a 0 and then came here. So you see, when can you come into this row? So here means that you haven't seen any 0, and then from here you can come here. So if you see some 0, right, and once you are here, okay, so if you see another 0, then you move to this place where you have seen 2 zeros. Otherwise you are seeing only once, so you move this way. You are processing symbols, but you have seen only 1 0, right? So it's very easy to map, right? So if you have seen, say, 1 1 0 1, so what will you have? 1 1, so that no 0. Then you have seen 0, that means you come here, and then another 1, then here. So if you then see another 0, then you complete these 2 zeros via this and this, and you are in some accepting state, right? So and you may not have, as I said, 5 symbols in that block, or even before you read all the symbols, perhaps you have already seen 2 zeros. Maybe you have seen 1 0 0. So you are already in this thing, and everything after that is accepting. So no matter what you see here, it's okay. Okay, so so there is one problem here. So here I need to put zeros also, because here means you have already seen 2 zeros. So after that it doesn't matter whether you see 0 or so. There I should put 0 or 1. Okay, so just make this correction. So here it should be 0 or 1. Okay. Now you are here if you have completed some block, right? Then you read some symbol again. Suppose you have 6 symbols. So after reading 5 symbols, you are here, and then again you have some other symbol. So if that symbol is 0, that means what? In the next block. So you are reading the symbol for next block after this. So if you see a 0, that means in the next block you have already seen a 0. So you are in this position. So that means you have seen the first symbol of the second block, and that symbol is 0. So you go to this thing. And similarly, if you have seen 1, that means you are in the second block, you have read the first symbol, and that symbol is 0. So that means, is 1. So that means you haven't seen any 0. So you are here, right? So this means that this means the start of the next block, which is either 0 or 1. So this is used only when you start the machine, when you haven't read any symbols at all. So that is where this is used. After that, you will not come back to this thing. So this is the meaning, and then I mean, if you are asked to prove that, okay, prove that this machine actually accepts this language, so then you have to do induction, right? And in the induction, this is the property you need to prove for all input string. And if your input string is w, the induction the induction parameter will be the length of w, right? So on the length of w, you prove all these things using induction. So that is the kind of only tool. Okay. So